Alright, let's take a look at section 3.6, polynomial and rational inequalities. Let's begin by looking at the definition of a polynomial inequality. A polynomial inequality is any inequality that can be put into one of the forms f of x less than 0, f of x greater than 0, f of x less than or equal to 0, or f of x greater than or equal to 0, where f is a polynomial function. Now let's take a look at the procedure we'll use to solve polynomial inequalities. So the first three steps of our procedure involves expressing the inequality in standard form. This basically means the polynomial f of x is on the left of the inequality symbol, 0 is on the right. Then I'm going to solve the equation f of x equals 0. Any real solutions to this equation are boundary points. I'm going to locate these boundary points on a number line, and this will result in the division of the number line into intervals. So let's apply these first three steps to exercise 40, where we want to solve the polynomial inequality and graph the solution set on a real number line. And we want to express each solution in interval notation. So x cubed minus x squared plus 9x minus 9 is greater than 0. We want the x's that make this expression greater than 0. That's what we're actually looking for. And this is already in the form that we want. The polynomial is on the left of the inequality symbol, 0 is on the right. Alright, now we want to solve this polynomial equal to 0. And we're going to do that by factoring, and we're going to factor by grouping. So I factor x squared out of the first two terms, and that gets multiplied by x minus 1. If I were to use the distributive property, I would multiply x squared by the difference x minus 1, I would regain these first two terms. Now I want to factor out the GCF from the last two terms that multiplies by x minus 1 and gives these last two terms. So x has to be multiplied by positive 9 for me to get this third term, positive 9x. So it's a positive 9 that is multiplied by x minus 1. And I double check that that actually gives me that fourth term. Positive 9 times negative 1 is negative 9. And I am going to use colors to illustrate this next step. So I'm going to put this x squared and this positive 9 in color. And I just want to point out that x minus 1 is actually our common factor. And notice how in first position that was multiplied by x squared. In second position that was multiplied by positive 9. So the only way this product can be 0 is if each of the factors is 0. So for this product to be 0, x minus 1 has to be 0, which means x is 1. Or x squared plus 9 is 0, which means x squared is negative 9, which means x is plus or minus the square root of negative 9, which equals plus or minus 3i. And remember, only real solutions are going to be boundary points. So I wind up with exactly one real solution, and that is my only boundary point, x equal to 1. So the third step in the process was for me to divide the number line around the boundary point. So here we do that here. Let me try this again. We will take the real number line. So this is that third step. And we will divide this up into intervals around the boundary point. So this first interval is the interval from negative infinity to 1. The second interval is from 1 to infinity. Here are the remaining steps in the process. I want to choose one representative number called a test value within each interval and evaluate f at that number. If the value of f is positive, then f of x is greater than 0 for all numbers in the interval. If the value of f is negative at this test number, then the function is negative for all numbers x in the interval. Once I complete step 4, I'll be able then to do step 5, which is to write the solution set, selecting the interval or intervals that satisfy the given inequality. This procedure is valid if I replace less than with less than or equal to, or I replace greater than with greater than or equal to. However, if the less than, equal to, or greater than or equal to symbol is part of the inequality, in the solution set, I then include the boundary sets, the boundary points in the solution set. So let's take a look at this, applying these steps to our problem. Now recall that this was our inequality. The first presentation of it, x cubed minus x squared plus 9x minus 9 greater than 0, gives it in its original standard form. The second presentation of it gives it in factored form. So this is also can be thought of as the quantity x minus 1 times the quantity x squared plus 9 greater than 0. Now remember, we had divided our number line up into two intervals. The interval from negative infinity to 1 and the interval from 1 to infinity. Now whenever you set up these test intervals, they never include the boundary points, even if your inequality is a less than equal to or greater than equal to, because the numbers you want to test here are numbers that are not boundary points. So these test intervals will never include the boundary point. If I have a less than equal to or greater than or equal to inequality, I'll include the boundary points when I give the final solution. So I've selected two test numbers in each interval. One thing you have to be careful of here is that the test numbers you select really are in your interval. So I'm going to test x equals 0 for the leftmost interval, and I'm going to test x equal 2 as the test value for the rightmost interval. And I'm going to test these in the factored form. So I'm multiplying 0 minus 1 times 0 squared plus 9. And I essentially want to know, is that true or false when I set that greater than or equal to 0? I mean greater than 0. So when I replace my test value with, I replace x with my test value, do I get a true or a false statement? So I wind up with -9 greater than 0. Well, that's false. So that means all the numbers in this interval will make the inequality false. So now let's test 2, our test value 2, and let's see whether or not that makes the inequality true or false. So 2 minus 1 times 2 squared plus 9 greater than 0. So 1 times 13 gives me a true statement. So this basically means all of the numbers that are bigger than 1 will make the inequality true. So the solution set is the interval 1 to infinity, not including the 1. And I was asked to graph this. So I start with the number line. I put a parenthesis above 1 on the number line. And I shade to the right of that. And I show with an arrow that I can move indefinitely to the right. So that's my solution set and my graph. If this had been a greater than and equal to, the only thing I would have done differently is when I wrote the solution set, I would have included the boundary point of 1 by writing this with a bracket. And on the number line, I would have put a bracket above 1 instead of a parenthesis. And you can show more numbers on the number line if you want, but you don't want to waste time showing a bunch of unnecessary numbers. The only number really required to show is the boundary point. Sometimes I see people and they've marked off 15 or 20 numbers on here, when really the only one really required is the boundary point. If you want, you can show 1 or 2, maybe 3 other numbers in their correct positions relative to that boundary point. So this is how I would solve, this is an example of how I solve a polynomial inequality.